Hello everyone, welcome to 8th week of this course. What we will be doing today or this week is we will apply method of consistent deformation that we have at least the concept of method of consistent deformation we learned in the previous week. We will apply that concept to various structures. This week we will be applying the method of consistent deformation for trusses, and the next week we will see how the method can be applied to beams and frames. Okay. So, so today we will see how the concept can be applied to method of can be applied to indeterminate stresses, finding support reactions and internal forces. Let us demonstrate that through one example. This is probably one of the very simplest example. If you remember, when we discussed analysis of statically determinate truss, we also started with the same example, but in that case the structure was statically determinate, but in this case it is an indeterminate structure, which we can easily identify by just looking at the structure. The number of support reactions provided here 4, but for the stability of the structure we need actually 3. One hinge support and one roller support would have been enough for the stability point of view, but still instead of roller support one additional the hinge support is provided. So, so it is an indeterminate structure. So, what we need to find out? We need to find out what are the support reactions and member forces by using method of consistent deformation. Okay. So, in the last week we discussed different steps for method of consistent deformation. Now, what we do is we just follow those steps. So, step 1 was determine the degree of static indeterminacy. Let us find out what is the degree of static indeterminacy for this problem. We know for truss the static indeterminacy is m plus r minus 2j. Where m is the total number of members, r is the total number of reactions, and j is the number of joints. So, in this case m is equal to 3 members, r is equal to 4, 2 here and 2 here, ax ay and cx cy, and then minus 2 into number of joints are 3. So, this is 3. So, this become 1. So, static indeterminacy for this problem ns is equal to 1. Okay. So, this was the first step. Now, next step is, once we know what is the static indeterminacy, next step is to identify the selection of the redundant force or redundant moment. So, in this case the moment is not relevant, because truss is all the members we can have at MD joint we can have 2 translations. So, either force in x and force in y direction, and if you take any member, the force in member is always along the axis of the member. So, in this case we need to identify what is the redundant force. You see, this is the step the most important in the entire process, because the step before this and all the steps after this they were in some way mechanical. They are you need to just follow the procedure. Once you know the procedure, then you can do that. But this is the step, the second step, where you need to identify the redundant force. There is some sense of structural analysis, some sense of stability, some sense of configuration or overall behavior of the structure is required. For example, in this case, you see there are 2 possibilities. This is a symmetric structure. Suppose we want to take one of the reaction as redundant force. Okay. Now, suppose consider joint C. So, at joint C we have 2 reaction. One is Cx and one is Cy, right. So, either we can take Cx as redundant or we can take Cy as redundant. We can take Ax or Ay as redundant as well, but this will be same because it is a symmetric structure. So, we can take either Cx as redundant or Cy as redundant. So, let us see what happens if we take Cx and Cy as redundant forces. Okay. So, first case is first possibility is this. Okay. First possibility is this. In this case, what is the release we have given in this structure? So, suppose C is now allowed to move in this direction. C is now allowed to move in vertical direction. C is now allowed to move in this direction. in this direction. Okay, the point C is allowed to move in this direction, but the movement in this direction, is restricted. So, this is allowed to move in this direction. Okay. So, in this case we have taken C y as redundant. Okay. Now, then next possibility is this. Next possibility is this. Okay. In this case, what happens? In this case, you see, the structure can move in this direction. The structure can this point C can move in this direction. This is allowed, but the movement in this direction is restricted. In original structure, the movement in both the direction is restricted for C. This is also restricted and this is also restricted, but in case 1 we allow this, and case 2 we allow this and restrict the other one. Now, let us see. So, this is case 1 and case 2, and both the cases we really do not know what case will be the possible case, but as per as theory, in both the case is at least as far as the, if we consider, if just the choice of if the point is select any redundant select any reaction as redundant force, the both two cases, case 1 and case 2, both the cases seem to be fine, but actually they are not. Let us see why they are not. Now, if we take first consider case 1. Okay. So, this is case 1 where this movement is allowed and this is restricted, and suppose this, if we apply any load like this, if we apply say any load like this, okay, any load like this, then what happens? This structure and let us see how this structure may deform. This structure may deform like this, you see. So, this joint C can move in this direction, but the movement in this direction is restricted. Now, this is unstable. Okay. So, this is unstable, and therefore, this configuration, the case 1 cannot be possible. So, this is not a possible choice. Okay. Now, if we see second case, is case 2. Case 2 is where this motion is restricted, but C can move in horizontal direction. Then what is the movement if it is applied to some load like this? If it is applied to some load like this, then it can move in this direction, and this configuration is stable configuration. So, which configuration is stable configuration? There are two ways. One is you take any configuration and write the equation, and then you find that the structure is not stable. But instead of finding or understanding the structure is not stable through that exercise, it is always better to develop the sense, that engineering sense, so that just by looking at the structure and looking at the force and the configuration of the supports, you can identify that which configuration will be stable configuration. And the stable configuration, you take any force as redundant force, but the primary structure after taking the redundant force, after removing the redundant force, allowing the deflection in corresponding direction, the primary structures that you get, that should be statically determinate and should be stable. Okay. Now, so case 2 is the possible case. I suggest you take both the cases, case 1 and case 2, write the equations of equilibrium and try to find out whether which step is stable and which is unstable. Okay. Now, so we'll consider case 2. Okay. So, the step 1 was the calculation of static indeterminacy we have done, it is 1. Step 2 was identifying the support reaction, identifying the redundant forces. So, we have considered these identify the redundant forces and then get the configuration of the primary structure. So, this is our primary structure, and the next step, the step 3 is, if you remember, solve the primary structure subjected to the actual load, and then step 4 was solve the actual primary structure subjected to the redundant force. Let us do that. Okay. Now, so this was the first is step 3. First we will do step 3. Step 3 is solution of the structure and analysis of the structure subjected to actual load. So, this was the structure, this is A, this is B and this is C, and it is subjected to a load P at B. Okay. Let us give some name for this all these members. Okay. Let us, this member is 1, this member is member number 2, this member is member number 3. Okay. One way of identifying member is member AB, member BC, member AC, but just for to make it convenient to write these the identification of the member, it is better to give some number to the member. So, member 1 means AB, member 2 means BC and member 3 means AC. Okay. It will be easier if in this case it is only 3 members, but if you any structure you can have many members, many joints. So, for those cases it is easier to identify members through numbers. Okay. So, these are the and then we have a support here. This is hinge support and this is roller support, right. We can we have already solved this structure. If you remember when we discuss about how to analyze statically determinate structure and the solution, we are not doing that exercise once again. You go back to that lecture and see what is the solution of this this problem. So, the solution of this is your support reactions are like this: AY is equal to P by 2 and Cy is equal to P by 2, Ax is equal to 0, Ax is equal to 0, okay. Ax is equal to 0, and the forces in each members are like this. Member 1 is equal to, okay, let us draw the force diagram. The force diagram is like this. This is the force in member 1, then member 2 and then member 3. We have already done this in second week. Please see that lecture, and this value is P by root 3. This is also P by root 3 and this is P by 2 root 3. Okay. So, this means this member, this is member 1, member 2, member 1, member 2 and member 3, right. So, member 1 is subjected to compression and the value is P by root 3, it is also compression P by root 3, and member 3 is subjected to tension and the value is P by 2 root 3. Now, if you remember unit load method, so this is the structure subjected to actual load. So, we write Ni N1, which is the member force in member 1, it is minus P by root 3, then N2 is equal to same minus P by root 3, and then N3 is equal to P by 2 root 3, P by 2 root 3. This is the forces members when the structure is subjected to actual load. Okay. And when we use the convention of unit load method. When we discussed that method, if you remember, we mentioned the method is a very powerful method and it has huge application in most of the subsequent methods that we learn in this course. So, let us, and the usual notation is when the structure is subjected to actual load, then it is written as N1, N2, N3, and then it is or capital letter M1 M, if it is moment, then M1, M2, M3, and if it is when is subjected to unit load dummy load, then it is written as small letter. So, this is step 3, then take step 4. Step 4 is the same structure is now subjected to redundant force. Okay. So, draw the same structure. So, let us this was step 1. Okay. So, draw the same structure, it is hinge support, it is roller support, and then this is A, B, C, this is member 1, member 2, and then member 3, and this is subjected to a load like this, okay, because that is the redundant force. Okay. Now, instead of applying a force Cx, which is the redundant force, support reaction at C in the direction x, let us apply an unit load. Okay. The reason is, if we know the value at the unit load, what is the member force in a support reaction, those values if you multiply it by Cx, we will get the corresponding member force in a reaction due to load Cx. Okay, because load displacement, those relations are linear, we can apply the method of superposition. So, this is the second, this is another, this is again determinant structure, but in this case it is subjected to redundant force of value 1. So, let us analyze it, and if we analyze it, then you see, by just looking at this structure, we can say consider this joint. If you remember, we again when we analyze this truss, first thing we see if we have some information about the truss or not. If you can reduce our problem, our computation. In this case, one way is identify the if there are members which have zero force, okay, zero force members. Now, if you look at this structure, then this member and this member AB and member BC, they are zero force member, because if you take joint B, then you can apply the free body, you draw the free body diagram of joint B and apply the equilibrium condition, you get this member and zero force member. But again, instead of doing that, just by looking at the truss, you should be able to identify what are the zero force members. So, these two members are zero force member. So, our problem becomes easier. Let us now draw the free body diagram of supports of C. If we draw the free body diagram of C, then free body diagram of C will be this is point C, and this force is 1, and this force is F AC, which is also is equal to N3 means the actual force in member 3 or FAC. So, apply, so this is FBD of C. Okay. Now, apply summation of Fx is equal to 0, and this gives us N3 is equal to 1. N3 is equal to 1, right? N3 is equal to 1. Now, then if we draw the entire free body diagram of the entire structure and apply the summation of Fx is equal to 0, and we will get Ax is equal to we get Ax is equal to again minus 1, okay, and then Ay is equal to 0 and Cy is equal to 0. We can get it, please check this. Okay. Now, then what we have here? We have N1 is equal to 0, N2 is equal to 0, and N3 is equal to 1. Okay. Now, instead of 1, if the structure is subjected to Cx, then the corresponding forces in member will be N1 0, N2 0, and N3 will be 1 into Cx is equal to Cx. Okay. Now, step 4 is done. Then what was the next step? Next step was apply the compatibility equation. Okay. Now, what is the compatibility condition in this case? You see, in the primary structure, because of this load, the C will the movement of C in this direction is allowed. So, because of this load, the C will move in this direction slightly, and similarly because of this unit load here, C will move in this direction slightly. So, total deflection, total deformation at C will be total movement of support displacement at C will be this plus this, and the compatibility condition says that because in the original structure this point was hinge support, there should not be any deflection at C, at deformation at C. So, compatibility equations say that deformation obtained from this and deformation obtained from this, their summation should be equal to 0. So, suppose this is delta C 1, this is, suppose this is delta C H, this is delta C H 1, means the horizontal displacement at C in this structure is equal to delta C H 1, and the suppose this is delta C H 2, horizontal displacement at C in this structure should be equal to, it is delta C H 2. Then step 4, compatibility equations say that delta C H 1 plus delta C H 2, they should be equal, that should be equal to 0. Okay, let us, but before we apply compatibility condition, we need to find out what is delta C H 1 and what is delta C H 2. We simply apply the unit load method, and if you remember the unit load method, the unit load method says that delta C H 1 will be, delta C H 1 will be summation over I is the 1, in this case 1 to 3, because there are only 3, there are 3 members, okay, and then Li divided by AEI, but in this case A and the cross sectional area and Young's modulus, they are constant. So, we can write AE here. Length of Li is different for different members, then Ni into small n I, that is unit load method, right. We discussed, in fact, we applied this method to truss problem in one of the previous weeks. Okay. Now, if we apply that, then what we get, that is equal to okay. So, A 1 by EI we can take it out, 1 by E. Please remember, if EI is AE is not constant, it is different for different members, then that also you need to write, this is for different member you need to write here, but in this case it is constant, that is why you can take it out. So, this would be then L1 into N1 and then you can take it like this, plus L2 N2 and then plus L3 N3 small n 3. Okay. Now, you see here we have already determined N1, N2, N3 and small n1, small n2, small n3. So, small n1 and n2 are 0. So, this cross this 0, this into this 0. So, what we are left with n3, small n3, and that is equal to, so 1 by AE. This part will be 0 because N1 is 0, this part is 0 because N2 is small n2 is 0, and this part is L3. L3 means length of this member, which is capital L, which is L into cap N3 is equal to P by 2 root 3 and into 1, small n3 is equal to 1. So, this becomes P by 2 root 3 A E, that is delta C H 1. Okay. Delta C H 1 is this. Okay. Now, we need to find out what is delta C H 2. Now, delta C H 2, that will be equal to same way. You see here unit load is here, if it is applied to unit load, then this is the these are the deflection. And now, if it is not unit load, if it is Cx, then the deflection, then the corresponding member forces will be 0, 0 and Cx. So, in this case, again I is equal to 1 to 3, and then this is Li by AE, which is Li is the length at different members, and then now unit load for dummy load, this is the result, and for actual load, in this case actual load will be Cx applied here, the result will be 0, 0 and then Cx. So, this will be say Cx into Ni, which is the member forces when actual load, in this case actual load is the dummy force Cx is applied, and then due to unit load which is Ni. Okay. That is, so this becomes, if we take Cx by A out, Cx by A out, and then this becomes Ni square. Now, N1 and 2 are 0 and N3 is equal to 1. So, this become 0 plus 0 plus 1. So, this become, so delta Ch2 become Cx by A E. Okay. Cx by A. Okay. Now, if it is, now next compatibility equation is this plus this should be equal to 0. So, step 5. Step 5, compatibility equation. Compatibility equation says that delta Ch1 plus delta Ch2, that is equal to 0. Now, we know what is delta Ch1 here and delta Ch2 here. So, write it. Delta Ch1 was L by delta Ch1, there is a correction, it will be P into L, there should be L here, okay, and there also there should be one L here, because it is L, okay, this is L here, this is L here, please correct it. So, this is PL by 2 root 3 AE, and then delta Ch2 is Cx into L by AE, that is equal to 0, and from that we get Cx is equal to minus 1 by 2 root 3 or P by this. Okay. Cx is equal to this. Okay. Now, if you draw the actual structure, this total structure, and this is A, this is B, this is C, and the free body diagrams are, this is subjected to a load P, this is AY, this is AX, this is CY, and this is CX. Okay. Now, there were 4 unknown, but now Cx is known. Cx is known. So, once you know Cx, then rest is you apply other 3 equilibrium condition, take summation of Fx is equal to 0, summation of Fy is equal to 0, and summation of Fz is equal to 0, summation of moment is equal to 0, we get what is the value of other support reactions. So, if we do that, if we take summation of Fx is equal to 0, this gives us Ax is equal to minus Cx. So, Ax will be P by 2 root 3. Okay. Ax is equal to this. If we take summation of Fy and mz is equal forces, summation of force in y direction, and summation of moment is equal to 0, we get Ay is equal to Cy is equal to P by 2. Okay. And rest the thing is you take free body diagram of every joint and calculate the member forces. Okay. Now, that was step 6. So, step 6 was once we have this reaction, once we have Cx, then apply the free body, apply the equilibrium, draw the free body diagram and apply the equilibrium condition on these structures to get the other unknowns, in this case other support reactions and the member forces. Okay. So, these were different steps for demonstrated for this problem, Okay. Now, demonstrated for this problem. Okay. Now, you see, it was a very simple problem, only 3 joints, 3 member, and supports are also the degree of static indeterminacy was also 1. So, we needed only one redundant force. That is why we could do it like this. No, but in a structure when you have where we have many indeterminates, when many redundant forces, many members, many joints. So, the concept is same, but the calculation in this way may not be. It becomes tedious. So, in that case, either we can write in a matrix form or a tabular form. Those things we will see in the next class. We will take slightly complicated problem, which has more number of where static indeterminacy is more than 1. So, number of redundant forces are more than 1. We will see how that can be solved using method of constant deformation, but the essence of the method is still the same. But in this case, again, the unit load method plays a very crucial role. We discussed that in one of the previous weeks. Please go through them and make yourself comfortable with the method, because very often in all the problems that we will be doing next, the unit load method plays a very important role there. So, please revise that. We will stop here today, and next class what we do is, next class we will see some more examples on trusses, analysis of trusses using method of consistent deformation. Thank you.